Hey, good morning. How is everybody? Can you hear me? Are we here? Hey, people can hear me. Good. Awesome. Tired? Yeah, isn't it weird, like, if you've been able to sleep in over a break, trying to get up early? Alright, well, people who are here, I guess, got the memo that, that we're starting off online this week. Hopefully switching back to in person next week. But we'll see how things play out. Alright, well, welcome to winter 2022, goodbye 2021. Welcome to CSE222. This is your data structures in C class. We'll be using pretty exclusively C. For the course, we won't be doing anything with bash in particular, but of course you can still use bash yourself to, you know, wrap your tools inside scripts and stuff. But this is a programming course. It's done almost entirely in C, and the focus of this course is data structures, which we'll be talking about, you know, later on today and Wednesday. But it's an intense programming course. We don't teach programming in C in this course. You're supposed to already know how to program in C at this point. Particularly after 224. You should be pretty comfortable with programming, and you should be comfortable with the mechanics of C, and we're going to talk about more advanced concepts in C, pointers and addresses and allocating memory and things like that. But basic programming, loops, conditional statements, stuff like that, you need to have a handle on that already, because we're not going to spend a lot of time going through those things. All right, so let me start off with just going through the syllabus. So this is an in-person class, Mondays and Wednesdays, 10 o'clock to 12:10. But as I mentioned in the announcement and in the email, and I'll mention here, right, I decided for the first week I'm going to go remote. A lot of schools are doing this around the country. Clark is not, but I didn't want to take the chance personally, and I didn't want to force people to come into class and take the chance themselves of being exposed. So first week we're going to stay online, and hopefully we're going to get back to in-person a week from today. But we'll see what numbers do between now and then. But I'm very anxious to get back to in-person instruction. All right, so let me run through the syllabus, and I'm just going to do this from my PDF instead of Canvas. So data structures course, right? C programming. You can read the details in here as well as I can read them to you. There's a textbook for the course. It's available online. It's a free download. It's a good treatment of data structures, but none of this stuff is new. This stuff has been around for decades. You don't need a 2021 book on data structures to understand data structures. So any resource you can find will work. I'm not going to assign homework from this book, but it's a free download. It's a good PDF. I recommend having a copy of it on hand to look at. And there's some other text here. Corman is sort of the gold standard for algorithms. and there's a lot of data structures and algorithms we won't be going over, but that you'll encounter down the road, and Corman's a good reference for all of those. C primer from good old CSE222A is good to have, and some sort of Linux text. All right, we will be using the Linux server somewhat, not a whole lot, but I'll be grading your programming assignments on the Linux server, and so you want to make absolutely sure that when you run your makefile, the executable you get on linuxengrcs.com runs correctly. Don't develop this in your own environment and then just push it out to Canvas and assume it's going to work for me. So you at least want to use the Linux server to test your final submission. So everybody who was registered for the course as of Saturday should have an account. There were 3 new students who weren't in 224. If you were in 224, your account is still there, no changes. If you weren't enrolled in 224 in fall, you have an account on this machine, linuxengrcs.com, and I'll point you to the login instructions in a few minutes. As with 224, I recommend having access to Linux on your own system. Either have a Linux laptop or install virtual machine on your Windows or OS X system and put Linux on top of that. You can read the course outcomes. These won't necessarily mean a whole lot until we get to these, but these are the topics that we're striving to attain mastery of by the end of the course. There's a different view of the topics we'll be covering. A lot of the rest of this is stuff you've seen before. Course policies, academic honesty, and plagiarism. So, same as always, do your own work. Do not use online resources. Do not take code from online sources. Do not take code from other people. Do not share or show your code to other people. If somebody turns in your code, you both get Fs. Okay? Don't, right? If you got any doubt, ask me about it. Hey, this person wants to do such and such. Is it okay if I show them this? Can I tell them about that, right? Come and ask me before you do it. If there's any doubt about what constitutes cheating, ask your instructor. And hopefully this doesn't happen, but just in case, right? So if there's any incidents of this going on, if you turn in an assignment and the code matches somebody else's, or the code matches an online source, or the code matches something that a student turned in 3 years ago, right? You get a 0 on the assignment, and we talk. Okay? If it happens a second time, it's an F in the class, and that's it. You're out of the course. Okay? I don't expect that to happen, but that's stated up here. If there's any dispute about what happened, if I say, this looks exactly like what this other student turned in, and you say, no, I wrote it on my own, I'll just turn it over to the honor board, and they have the resources to take statements from people and try to figure out what happened. So all right, hopefully all of that's a non-issue. Late assignments. So we're going to have 4 slip days this quarter, and I'll talk more about those in a few minutes. Support services, I've already got a number of students who are taking advantage of this, but if you feel like you need some sort of accommodation, extended testing time, low distraction testing, a Notetaker in class, anything like that, talk to the DSS office or talk to me and I'll give you more information, and accommodations can be set up. Non-discrimination policy, you've all heard me read this before. I'm not going to read it through verbatim, but make sure you read this, okay? This applies to every class that you take on campus at Clark. Title IX and sexual misconduct, we've got more details of that in here, so make sure you read through this. College-wide student information is available at this site. Help is available financially, with food, with housing, things like that. We're still in a global pandemic, and things are probably getting worse for the next few weeks at least, maybe the next few months. If you're having trouble making rent, paying tuition, having enough food, whatever, right? There's help available, um, and Kath is the main contact person to talk to. There's their email address. Um, but you can go to this website and see some information on what's available, but send an email to Kath and they can set you up. All right. This will become topical next week, hopefully. So COVID-19 mitigation efforts, since this will be an in-person class. Everybody needs to read this. Okay, it's a state requirement, but I'm not required to test you on it. So you're kind of on your honor that you're going to read this over. But basically, I think most people are familiar with this. So you have to do your daily health screening before you come to campus, right? Hop onto that website right here, answer those questions, answer them honestly, okay? And make sure you're cleared to come in. When you're on campus, you need to stay 3 feet from anybody else, okay? You need to wear a mask at all times, anytime that you're in an indoor space. When you enter the classroom, there'll be hand sanitizer available. Please wash your hands with that. And then at the beginning and the end of each class, you're asked to use the cleaning supplies to clean the area that you're sitting at. So there'll be like, Clorox wipes or something, and gloves, I believe, and use those to clean the area. Okay, this next part is super critical though, right? If you think that you might have a cold, right, stay home. Okay, if you're not sure what your symptoms mean, if you're feeling kind of out of it, if you're sniffly and you don't know why, right, stay home. Okay, I'm not counting attendance this quarter. The classes are recorded. Don't take chances, all right? If we come back in person and we start getting case counts in the classroom, we're going to end up remote again. Okay, so we don't want that to happen, and we don't want you to take chances and push yourself if you're feeling sick and stuff. So if you're exhibiting any symptoms, mention in the questionnaire, stay home, send an email to me, let me know what's going on. All right. Everybody needs to be vaccinated unless you have an exemption on file, and if you haven't already done one of those things, you would have been dropped from the course. So if you're here, presumably you've taken care of this. May move from face-to-face to remote. We've already done that today, so none of that's going to change. But just to be clear, right, if we go remote, we're meeting at the same time, same days as if we're in person. And when we go back to in-person, it's the same days, same times, except we're going to be in SPG 155 when we're back in person. You got to wear your mask in the class. You got to keep your mask on. You're not allowed to eat or drink in class. If you need to get a drink, you can step outside and go to the fountain or take a drink or whatever. Social distancing, sanitation, no eating or drinking in classrooms. All right, and then 2 more links to click through: Code of Student Conduct and ECS course policies. And you've seen these on other syllabi as well. Let's see. Let's see. If you were enrolled in 224, you should still have an account on Linux. If you were enrolled as of this weekend, you should have an account on Linux. So try the login. If I'm sick, can I stay home and watch an in-class lecture via Zoom? No, I will not be Zooming these when we're in person. I don't think we have the bandwidth on campus to do that, and I don't have the logistic wherewithal to do that. But you'll be able to watch the recorded lectures if you're staying home. All right, so that's syllabus. Additional course policies is the particulars for this this offering of the class. So where does your grade come from? All right, you're going to have 5 programming assignments. Those account for a total of 30% of your grade, so that's a major portion of your grade. There's some online quizzes on Canvas. You can take those anytime before the deadlines. That's 10% of your grade. Midterm will be 20, final will be 30, and the service learning project will be 10. So pretty straightforward assessment calculation. You can read through the keys to success on your own, and I'll allude to these throughout the term, but glance through these, right, and make sure that you've at least seen them so you can think back to them. But the main one I will mention is, you know, come to class, come to every class, come on time, stay for the whole class, participate as much as you can, right? If you say, well, I'm just going to watch the lecture after class instead, you won't do it, right? You'll fast forward through it, you'll skim it, and eventually you'll just end up going back and looking through the lectures to try to find what you need, right? Come to class, right? And spend the time, spend the energy. And if you learn the stuff during class, then you don't have to spend, you know, all that time trying to figure out what's a pointer, you know, what does this ampersand mean, right? You can learn it during class, or you can ask questions about it during class. So read through these, and you know, you've seen these before. I've talked about them before. Getting help. All right. Best way to ask for help is during class, right? We're meeting for over 2 hours on Mondays and Wednesdays. That's a long time. You don't want to listen to me just sit here or stand in class and talk for 2 hours. It's going to be really, really boring, right? Ask questions. If I'm talking about something and it's not making sense, stop me and say, hey, this isn't making sense to me. Can you re-explain it, or can you tell me such and such, right? That's the absolute best way to get help, to ask questions, okay, is during class. If you can't do that, catch me in office hours. Okay, I have office hours Thursdays, Tuesdays, and Fridays in the morning. There's a Discord channel for the course, and you're welcome to go there and talk to people about general questions. Don't go there and say, hey, can somebody look at my code and tell me what's wrong? That's cheating. Okay, don't do that. But you can go there and say, hey, you know, I don't understand what this means by cleanse the input. And someone can say, oh, that means, you know, convert everything to uppercase and get rid of spaces. Right? So explaining things that we've already talked about in class, you know, but explaining them maybe in a different way that helps somebody understand, that's a great use for Discord. Or looking at Garfield and the sock drawer fire is also good. So that's another option. You can try sending me email, but I'm going to make 2 disclaimers up front. One, I'm going to stick to looking at emails probably once a day, probably in the morning. And 2, emails are not going to work for back and forth, right? If you have a question that I can answer in email, I'll send you an answer. If you send me a follow-up, I'll probably get to it the next day. So I'm not going to do a lot of back and forth. In particular, I'm not going to get into email dialogues like, my code's not working, what's wrong with it, right? Well, usually my first question is, you know, what's it outputting? And that needs to happen in office hours, right? We can screen share, we can, you know, have you run your code, we can look at the source, we can try some experiments, we can hop into GDB. I will help you go through the debug process, but you're the one who's got to do the debugging. Okay, I can guide you, but I won't debug your code for you. All right, so plan on using office hours. If 5 hours a week of office hours are not enough, I can add more office hours just for this class. Okay, but you got to meet me halfway and come to office. All right, so stick to working in Linux. If you're going to university next year, you're going to be living, sleeping, breathing in a Linux environment, right? The more comfortable you get with it now, the better off you're going to be. And everything that we're doing this quarter, you can do in Linux. So stick to that. Avoid the IDEs, avoid code blocks and Visual Studio and all that stuff. Get down to the metal, right? Work on the command line. It's easy when you've been working on the command line for a few years to come back and start using something like IntelliJ, you know, that you can go to sleep and wake up and your code is written for you. It's very hard to go the other direction, to kind of, you know, develop your programming skills in these really powerful environments and then try to work on the command line. It's a really hard transition. So start off, you know, working low level. I'm not going to use Git for submissions, okay? we did Git exclusively in 224. Everybody should be comfortable with that. Everybody should be familiar with it. That will help you at the university, okay, where you're going to have to use Git, you're going to have to use it in Teams and so on and so forth. But it is fairly difficult for me to manage submissions through Git, particularly with slip days. So we're going to go back to submitting programming assignments through Canvas, and we'll see how that goes. However, I encourage you to continue using Git on your own, right? Make backups of your code, keep source code control, copies of old versions, things like that. It's still your friend, right? So keep using Git. All right, one-day programs. I'm not going to do ODPs this quarter. ODPs are difficult when we're not meeting daily, and they're difficult when I have two sections meeting on different days. And so that's one issue. Two, it's still a fair amount of work for me to do ODPs. And three, I feel like ODPs are starting to kind of miss the point. Like, it seems like students are using ODPs as kind of a replacement in some cases for learning the material instead of an aid to learning the material. And the ODPs aren't really the goal, right? The material that we're going through in class, the concepts you need for the programming assignments, those are the goals. And the ODPs are tools to help you, stay on track and learn the pieces of those. But ultimately, right, you need to be able to do that yourself. You need to be able to say, I don't quite understand scanf. Let me write some code and see what scanf does, right? And that's all the ODPs are. They're just a way to kind of force you to do that along the way. So what I'd like you to do is start thinking about, how can I do that myself? He showed us how to use an ampersand and a star today, and he did something with malloc, and I don't quite understand that, right? Well, sit down and take the code that you saw in class and type that in, and reproduce what we did in class, and then start changing it. What if I don't do this malloc? What if I put a different number as the argument to malloc? What if I swap the ampersand and the star, right? So this is what I mean by develop your skills at creating test problems yourself in order to better understand course concepts. And that's a really valuable skill, right, for the rest of your life, as long as you're doing anything in tech. Being able to sort of like, here's this thing I want to work with. I don't know anything about it. How do I learn what this thing does? How do I explore it? Well, it's by doing tests, So that's kind of like science. All right, another thing about academic honesty, which I won't go into. Late work. All right, so let's talk about slip days. All right, you get 4 slip days for the quarter, and you can use these for the programming assignments. You cannot use them for the quizzes. You cannot use them for the service learning project. You cannot use them for the exams. They only work for the 5 programming assignments. All right, and you can use them however you like. And you do not need to tell me when you're using a slip day. You do not need to ask permission. You do not need to apologize. Okay, these are for your use if something comes up and you're called away from your computer for an emergency, or you just need more time to figure out how to do something. You can use these slip days. Okay. And the way it works is we're submitting our assignments through Canvas, right? So you can be, doing your stuff on your own machine. You can be keeping copies on Git, all that kind of stuff. But when you are ready to turn in your program, upload it through Canvas. And once it's uploaded through Canvas, that's it. That's the version that I'm going to grade. If you upload another version, I'm still going to grade that first version. So make sure that your code is done before you turn it in. And once it's turned in, that's it. That's the assignment. And so you don't need to tell me if you're using a slip day, because if you submit your code 2 days late, I will record that as 2 slip days. If you can't get your assignment done, you decide, I don't want to bother taking any slip days, I'll just take a 0 on this, just don't submit it. And I won't charge any slip days. Does that make sense? So you don't need to ask about them. You don't need to You don't need to warn me about them. You don't need to adjust. You know, if you're going to take one slip day and decide to take two, you don't need to do anything about that. Just, you know, take as many slip days as you need and upload to Canvas when you're ready. And if you don't have any slip days left and you upload late anyway, right, it'll just be a 0, and I'll put a note saying, you know, no slip days. So yeah, it all happens automatically, which is great because, you know, particularly at the end of last quarter, I mean, I would have 70 or 80 emails from students talking about slip days and things like that, like, you know, in the morning when I wake up. So just for reference, right, here's a little table that might be helpful. So, you know, if you turn your assignment in on time, it's 0 slip days. If it's late, but less than 24 hours late, it'll take 1 slip day, right? That means if you turn it in 10 minutes late, it costs you a slip day. If you turn it in 23 hours late, it costs you a slip day. All right. 24 to 48 is 2, 48 to 72 is 3, 72 to 96 is 4, and if it's more than 96, you do not have enough slip days, so it'll be a 0. And again, you know, these are kind of intended to be there to take care of emergencies or unexpected events or something anomalous that happens, as opposed to, you know, I'm not ready to start programming yet, I'm going to push this back 4 days, you know. All right, other policies may be given in class, but this is the bulk of it. So any questions on any of that? All right, so there's an entry here for COVID-19 training. This is the thing that you're supposed to go through, and I'm not going to read through this with you right now. I've already looked through this myself, but make sure you go through this and have seen it and understand it. And if you have any questions, let me know. And there's a test you're supposed to take at the end, but like I say, I'm not required to do anything with your test results, so you don't need to submit anything, but, you know, take this test and self-check yourself to make sure that that you've got the ideas down. All right, Zooming info, you've already got that. Office hours. So engrcs.com/schedule. Always go there to see office hours. If anything changes, I will update there. But right now, I am Tuesdays and Thursdays from 8 to 10, and Fridays from 9 to 10. And it's the same office information, but if you click on more details, there's a link to Zoom and so on. All right, link to the lecture videos, topic list, video list, and shared code, same as usual. Let me mention again, there's another textbook in here called I Can See Clearly Now, okay? I wrote this text a few years ago for this course, okay? I wrote this to be a bridge between 121, 224, and 222. So I wrote it for this and 224. But this may help you, right? So some of this stuff, like using scanf to parse and things like that, were topical in 224. But there's a chapter on pointers, right? That's going to help you a lot with what we're doing in here. Bit flipping, recursion. These are all things that will come into play in 222. So take advantage of that if it seems helpful. All right, how-tos from CSE224. So if you were not enrolled in 224 in fall, and you're trying to figure out how to get onto the Linux server, there's information in here that tells you, right? So that's the Linux server, linuxengrcs.com. Your username is your first initial followed by your last name, and your initial password is your 9-digit student ID followed by an underscore. right? Nothing to do with the login that you used for CSE121. Different server, different username, different password. All right. If you cannot get into the server, let me know. Right. Come by office and I'll either reset your password or set up your account if it's not set up, and so on. Some online quizzes. The first one is due tomorrow. This is just a hello world. All right. So it's a one question quiz which asks what class are you sitting in. But I want to make sure everybody knows, that the quizzes are here and that you can do those through Canvas and so on. So get your 1 point today. Programming assignments. First one will be due a week from Friday. I will post this on Wednesday. So we'll have Wednesday to talk about it. You'll have a weekend to work on it, and then all of next week. Service learning project. So you should have started a service learning project in CSE222A. If you haven't, ask me about it. Right? I think everybody who's in here who wasn't in 224 took 224 a previous quarter. So same idea. We're going to have a service learning project. So you have a final upload week 9, which will be a PDF that you fill in from a PowerPoint, same as in 224. And then we're going to have an online presentation last Tuesday of the quarter. And so you get 50 points for each of those. Midterm and final exam. Midterm will be February 2nd. It will be from 10 o'clock to 10:55, so 55 minutes. Final exam is according to Clark's final exam schedule, which lists us on March 14th, 10 o'clock to 11:50. All right, important detail on the midterm and the final. These are going to be closed book. They're going to be closed computer. Okay, you will be allowed 6 double-sided pages of notes or 12 single-sided. And you can put whatever you want on those notes. You can put copies of your code. You can put, notes to yourself, examples, things like that. But that's all you get on the exams is your 6 double-sided pages of notes. And this is not as big a shift for this class because we're going to be in person. But for the remote class also, everything's going to be done from your notes. All your answers are going to be written out by hand. And for the online class, they're going to scan them and upload them. So no computer use allowed during the midterm or the final, other than to download the questions in the beginning and to upload your answers at the end. But if we're going to be in person, right, I will pass out pieces of paper stapled together with questions written on them, and you'll write your answers on the pieces of paper. It's a revolutionary concept, but we're going to make it work. What happens if we end up sick on the day of the midterm or the final? So make sure you have documentation, right? So something that can show that that's why you were out, and then we'll figure out how to do a makeup. But I'm going to insist on documentation for missing those, just out of fairness. And I do not want people to, wake up with a fever and say, oh, but I got an exam today, I'm going to go in anyway. Don't do that, right? Stay home and take care of yourself. All right, that's pretty much it for Canvas stuff. So any questions about any of that? All right, can somebody say something on their microphone? Because I want to make sure my sound is working on my end, and I haven't heard a peep from anybody. Okay, it works. Awesome. Thank you.
Nice.
Usually when the quarter starts, lots of stuff has changed, and things are broken. And so far, things seem to be working still, so that's a delightful surprise. All right, so we will probably take a break around 11 o'clock. We'll take 5 minutes just to, not go for 2 hours straight. All right, any other questions before we kind of jump into stuff?
Well, my question was that on campus, I still see my two classes computer science classes I took last quarter. Are you planning on removing them?
On
Yeah, note that as well. You can manually remove courses from your dashboard by clicking the courses button and then clicking all courses, and then you can star and unstar courses in there. It does look like, Nick, you may have forgotten to unpublish CSE222A from last quarter.
So that's very possible. But yeah, you can go to courses and all courses and hit the stars or clear the stars to make things appear or disappear. I don't close out my courses like the day after the quarter ends and stuff, because people like to go back and look at the exams and things like that. So I honestly don't know like when those courses go away, because there's like multiple rule sets that overlap. But yeah, you can make them go away from your view by just unpublishing. All right, let's talk about data, and data structures, and think about a typical program that you're writing, and there's sort of two pieces to your programs. There's code, there's instructions that are saying what the computer should do, and then there's data. It's the stuff you're manipulating. So if you're trying to calculate pi, you've got some temporary variables and a running sum and stuff like that. If you're trying to compute averages for a class, you've got a set of grades from students, and you've got a set of weights for different assignments, and you're doing weighted sums of those, and so on and so forth, right? So we're talking about the data part of this, not the code right now, right? Just the data itself. And we can think of data as here's some piece of data, and here's some other piece of data, and there's some more, and we can just think of these as here's some integers, and there's a string, and there's some other integers, and there's a floating point number, and so on and so forth. And that's kind of how we start programming. We just have a bunch of variables that we can do whatever with. But a lot of times when we're writing programs, our variables are not completely unrelated to one another. For example, if we had a program that was calculating grades for a class, what we might find is that we have a series of grades, one per student, and maybe we have a series of strings, one per student, where these things are the grades for each student, and these things are the names for each student. And maybe we have some other numbers that represent how many slip days each student has used. And so we might have a set of doubles, a set of strings, a set of integers, but it's not just a pile of data. There's relationships among these pieces of data. This third double is a grade which corresponds to the student who's named in this third string, who has used the number of slip days given by this third integer. And so when we make an array, what we're really doing is we're saying, hey, I don't just have a bunch of unrelated numbers. I have a bunch of numbers that are somehow all similar. They all represent, a grade. And they're ordered. This is the first one, the second one, the third one. And that order corresponds to the order of another chunk of data I have, which is a bunch of names. And that corresponds to a third chunk of data I have, which is a bunch of integers corresponding to the number of slip days each student has used. And so we're structuring our data when we put our data into an array. And in C, we also have this structure statement So I can say I want a structure called blah. And the structure is going to contain, you know, this variable of this type, that variable of that type, this other variable of this other type. And now if I make a variable and I say this variable is a variable of type struct blah, that variable has 3 pieces of information inside it. This piece, and this piece. And so this is another way in which we structure our data, our information. We're saying, hey, you know, this thing and this thing and this thing are not just, you know, 3 random variables scattered around in the memory of my machine. They're related to each other. They're all related to the same thing that I called, you know, a struct blah. And so what we're moving towards is a mindset where, in addition to the basic types of variables that we have in C, we have these new custom types of variables that we're creating. For example, I might have a struct student, which might have a double representing their grade, an integer representing how many slip days they've used, a char star representing their name, an int representing their ID number, and, you know, maybe some other stuff. And so I can make an integer I, which holds an integer. I can make a character C, which holds a character. I can make a struct student S, and S will hold a grade, a slips, a name, and an ID. So if I've defined what a struct student looks like, I can say struct student S. And S now has all these different pieces to it, so I can talk about this student's grade as s.grade. I can talk about their number of slip days as s.slips, and so on. Now, I don't have to do this, right? If we're writing in a language that doesn't support structs, we could still do something like this. I could simply call the student's grade, you know, s underscore grade, and I could make a new variable called s underscore slips, and s underscore name, and s underscore ID, and I could have 4 separate variables. And then when I wanted to pass the student information to an array, I could just pass all 4 of my variables. But this is a way to take these 4 pieces of information and combine them into a single thing. And so this S is now a new type of variable. It's not just an int or a char or a double. It's a composite of 4 different variables. So in 223, we would actually call this an object. But for now, I'll just call it a thing. But an object is really, you know, a variable that has more than just, you know, typically just an integer value or a character value or something. It's got lots of other stuff with it. So 223 in Spring will focus on object-oriented programming, but we're kind of doing the same thing in 222, but we're not calling it an object. And we're not using an object-oriented programming language, we're using C. All right, so we're gathering these things together. And this is necessarily going to make us talk about pointers. And pointers are things that people tend to get tripped up on in C. And you can find tons of videos on YouTube with people, you know, explaining pointers and drawing lots of good pictures and so on and so forth. But once you understand fundamentally what a pointer is, you've got pretty much the whole picture. the mechanics of how we use these mallocs, ampersands, asterisks, and all of that, those are not the real challenge. The real challenge is, what is a pointer? Why are we even talking about pointers? But the motivation for pointers is that, if we have some big complex piece of data, some variable that's really a big structure, right? We don't necessarily want to hand all of the bytes making up this structure to, a function, for example. And a pointer is a way to basically refer to where something is stored in the computer, instead of referring to the thing itself. And we use pointers, in 224 and 121. When we do scanfs, for example, we put those ampersands in front of arguments. And when we do strings, we know we're talking about pointers. But let's forget about those for a few minutes. And let's talk about pointers kind of by themselves. And I'm going to hop into GDB shortly, and we'll start using GDB more and more in this course to do some of these explorations. But let me give you the high-level view of pointers first. So in C, if I say integer I is just an integer, right? Anytime that I use this variable I in a statement, the compiler will write code which will cause the CPU to read the value of some memory location. So I will be stored somewhere in the memory of the computer, and when I say, print I, the print function will go to wherever this variable is stored, look at the bits stored in that location, use that to figure out what to print. Alright, if I say integer asterisk p, that's a little different. That's saying p is pointing to an integer. So what do we mean by pointing? We mean that p tells me where an integer is stored. But p itself is not that integer. P is the address of the integer. So like I, would be your friend's actual house. P would be the address of your friend's house. Right? And these are very different things. Right? This is the actual house that your friend lives in. This is, 100 East Main Street, Vancouver, Washington. It's the address of your friend's house.
Did you just dox yourself?
Did I what?
Did you just dox yourself?
No.
Aw.
Yeah. I don't know if there is a 100 Main Street. All right, so very different things, right? And if you have an integer, right? If you know a house, you can say, hey, what's the address of this house? You can go outside and you can look at the mailbox and see what the address is, right? In C, we can find the address by putting an ampersand in front of a variable. So this thing means the address of this variable I. So I could do something like P equals ampersand I. And now P shows me where I is located, what its address is. And you can do an ampersand in front of any variable, because every variable is stored somewhere in the memory of the computer. Doesn't matter if it's an integer, a character, a double, or even a pointer. Every variable is stored somewhere, and you can find out where it's stored by putting an ampersand. And so if we make kind of a fictitious memory map of a computer, and I'll use simpler addresses than we would actually see. Because usually these are like, 48 or 64-bit addresses. But But let's just say here's 8 locations in memory, starting at location 100. And let's say I've said integer I. Well, the computer might decide, okay, I'm going to store I down here at location 104. And so if I say I equals 17, the code that's written by the compiler, when it executes, would take the number 17 and store it at location 104. And if I say I equals I plus 1, the code that's been written by the compiler and is executing in the CPU will do the following. It'll say, okay, I know I is at location 104. Let me read what's at location 104. That's a 17. Let me add 1 to it. That's 18. Let me store that back where I'm storing I. Okay, I'll put an 18 here at location 104. Okay, that's life without pointers. That's just how variables work. But if I say something like this, integer star p, and I say p equals address I, what is p going to be equal to? Yeah, p is going to be equal to 104. Why? Because that's where 104, that's where I is stored. Here's the funny thing though, right? When I say integer star p, p is going to have to be stored somewhere in memory. So maybe that'll get stored here at location 102. When I say p equals ampersand I, it will say, okay, where is I stored? Let me think. Oh yeah, I stored it at location 104. Okay, I'm going to put a 104 right here. And so now our memory map might look like this. Let's make an integer j, so maybe j will get stored down at location 106. And now if I say p equals address of j, the compiler will say, okay, j stored at location 106. I'm going to set p equal to 106. Well, p is stored up here at location 102, so it's going to store 106 there. All right, everybody good so far? So the other thing we can do is if I have a pointer, I can say star p. And this means the thing that p points to. Star p says I'm talking about the thing that p points to, right? P is just p. It's just whatever the value of p is. It's 106 right now. But star p says, hey, I'm not interested in this variable's value. I'm interested in the thing at the address that p is pointing to. So if this is the address of your friend's house, star p is referring to the actual house. So if I say something like, you know, print star p, here's what the compiled code does. It says, okay, where's variable p stored? It's stored at location 102. What's stored there? The number 106. Should I print 106? No. I should print what's at location 106. I should come down to 106 and look at j. I'm going to print whatever is stored here. This star is sometimes called dereferencing a pointer. P, since it's a pointer, we can think of it as a reference to something, right? P is pointing to or referring to something else in memory. To dereference that pointer is to say, let's find the thing that it points to. In this case, we have no idea what this would print because we haven't stored anything at location 106. We said that j was an integer, but we never gave j a value. So this is, going to print who knows what, some random value. But if up here, after I said p equals ampersand I said print star p, well, at this point, I was equal to 104. This would have said, go to location 104, see what's stored there. That's the number 18. This would print 18. All right, just for completeness, let's make an integer star p2. So I don't know, let's suppose the compiler decides I'm going to store p2 at location 100. And now I'm going to say j equals star p2. If I just say j equals p2, that'll take whatever value is stored here and copy it to location 106. That's where j is. But since I'm saying star p2, right, remember that star says the thing that p points to. So here's what the compiled code will do. It will say, okay, let's look at the value of p2. Let's see what this value is and go to that location in memory. And that is what we're going to set j equal to. Well, what location in memory is it going to look at? I have no idea. We haven't given p2 a value yet. And so if I try to say star p2, this says, hey, take the value stored here, right, which is some unknown value, and go to that location in memory. Well, most locations that we might go to in memory don't exist. If this is a 0, that doesn't exist in memory. If this is, 93,007, that location probably doesn't exist in memory. So in most cases, if we haven't stored a value in here, a particular value in here, and we try to see what's stored at that location that it's pointing to, it's going to be looking at a location in memory that doesn't exist. And when we try to read from that, that's going to give us our seg fault. So this is the problem with uninitialized pointers. And probably the most common cause of seg faults in this class and in 224 is and was not initializing a pointer correctly. Now if I set my pointer equal to the address of something and then I use star pointer, that's going to work. That's going to be fine. Right, if I set p2 equal to ampersand p and then I printed star p2, I would get the value of p. And that's totally legit. A lot of times when we declare a pointer, though, it's initialized for us to 0. And anytime we try to look at location 0, we're going to get a seg fault, because location 0 doesn't exist in memory. All right, so before we take a break, let me do two things. First of all, let me remind you, I'm not doing attendance this quarter. Okay, so we don't need to do any attendance pings. Yeah, I'll probably pass around a sign-in sheet some days when we're in person, just for seating purposes and for contact tracing. But I'm not counting attendance for your grade, so don't worry about that. All right. So the other thing, I've been asked to read the following announcement to you. So a student in this class has a documented disability that impacts his or her or their ability to take comprehensive lecture notes. And so we're requesting that someone, preferably two of you, volunteer to share your notes. And since this will be an in-person class, I believe the way that they're doing this is the way they used to do it before COVID. Was you get special paper that's carbonless copy paper, and you take your notes on there, and it automatically creates a copy for you, and then you can drop that copy off at the DSS office, and they'll take care of distributing them to the students. So this is a service that would help out your fellow students, and I think we have multiple students in class with a note-taking accommodation. So if this is something that you would consider doing, send me an email, and this is an email I will respond to promptly. Send me an email and let me know. I'll send you a link you can use to register as a note taker, and then the DSS office will get in touch with you and help you figure out how to turn your notes in. Note taking is an essential part of learning, right? So this would actually be beneficial to you potentially, because it kind of would help motivate you perhaps to take careful notes. And listening to a lecture is fine and good, but the more active you can be in class, the more you're going to retain, the more you're going to understand, and the more likely you are to realize if there's something that you don't understand, that you can ask questions right then, right? And remember, the exams are a closed book, open note. So in addition to taking notes during class, what you'd really like to do is go through your notes after class and rewrite them, boil them down into the essential parts of it, because chances are by the end of class, some things that you wrote down earlier you'll already be totally clear on, right? Or some things you'll come to office and ask for clarification on, and then you'll add those to your notes. But your notes should sort of evolve throughout the course, so that when we get to the midterm, you don't have to figure out what to put on your note sheets. You should already have your note sheets. And as you're working through material in the course, as you're working on your programming assignments, you should be using your note sheets, right? Don't be going to Stack Overflow. Don't be going through the book. Don't be going back and watching lecture videos. Use your notes. And if you've got 3 or 4 pages of notes that summarize pointers and the malloc statement and things like that, right? Then you can use those as you're writing your code and debugging your code and so on. And when you find that you don't use this section of your notes anymore because you've done it 200 times and you understand it completely now, right? Take that out of your next version of your notes. And then for the midterm, really all you're doing is just rewriting your few pages of notes one more time with the stuff that you really think you need to have for the exam. So that's my sales pitch on note taking. But if somebody is willing to share their notes with others in the class, like I say, send me an email, and I'll get you the information on how to set that up. All right, so it is 11:03. So let's do a 5-minute break, and we'll come back and we'll hop into GDB and start playing with some of these concepts online. All right, so let's hop into GDB and let's play around with pointers and stuff. And GDB is going to be a really useful tool in general for this course because if we're doing things like this, we have a pretty good understanding, you know, of what P is. For example, P is where I is stored. And we know that star P is going to give us the value of I, and so on and so forth. We know that if we change star P, we're going to change the value of I, and things like that. But pretty quickly as we go through this course, what we're going to start doing is creating variables in memory that aren't there when the program starts. Right? We're going to on the fly, create new variables. And the only way we're going to have to really work with those new areas of memory that we've created variables in is to use GDB, or, you know, a ton of print statements, which we probably don't want to do. So let's play with this. All right, so let's well, I got stuff here. So I'm just writing some junk code here that we're gonna run in the debugger and see what happens. All right, this is going to complain a little when I compile, but I'm going to ignore the complaints. So I've got three integers, I, j, k. I've got a pointer to an integer p, and I'm going to set I and j equal to 20. And I'm going to set p equal to ampersand I, which is the address of the variable I. And then I'm going to print these things out, I, j, and k. Or I, j, and p. I'm going to print those out with %d. It's going to complain about this, but we'll print it out anyway. And then I'll set k equal to star p, print out the value of k, and then I'll set star p equal to 5 and see what that does. So let's compile this, and let's use the G switch for GDB, and we'll ignore the warning. So we're going to run this with GDB main, and, you know, we can see our source code here. And let me go ahead and start this. So we've hit a temporary breakpoint. So if I print I, it's, you know, some random variable. If I print j, it's some other variable. If I print k, it's some other value. If I print p, it's, you know, who knows what. So before we initialize variables in C, we've got, you know, essentially random values in them. So I'm at line 3, which is my curly bracket here. These don't generate executable code. So the next line that's going to be executed is I equals 10. So if I say next, it tells me it's about to do I equals 10, right? I still doesn't have a 10 in it yet. GDB shows you the statement that's about to be executed. So if I say next, this statement will fire. And now if I print I should be equal to 10. And the line of code that it showed me, line 8, which says j equals 20, that has not happened yet. So if I look at j, it's still got that weird big long number in it. But if I say next, that will execute j equals 20. And now if I print j, it's got, you know, a good value in it. All right, if I look at the value of p, it's this weird thing, 7, a bunch of f's, E440. I'm about to say p equals the address of I. If I execute that, and now I look at the value of p, it's got a different value. It's 7, a bunch of f's, E344. All right, so what is this number? This is a memory address. And you know, I can execute this print statement, and it shows me I and j and p while it's printing out p as a decimal number, which is kind of silly because it's actually, you know, a location in memory. It's an address. And a lot of memory addresses start off with a 7 followed by a bunch of f's. Why would it be 7 with a bunch of f's? What's the significance of that number? Or what do we know about that number? This is kind of an engineering 250 question.
About which number? Sorry.
The number that's highlighted right now, 7FFF, a bunch of F's, E344. But I made the comment that a lot of the times these things will start with 7 followed by a bunch of F's. And so what's significant about a hex number that starts with 7 followed by a bunch of F's? So not the
It's
whole
some
number, but
portion of memory that's
mm-hmm.
I don't remember what it's called.
Yeah, so it's definitely an address in memory. It's the memory address of the integer variable. This is true. So this is a hexadecimal number. It's got a 0x in the beginning. What would this look like in binary? Lots of ones, exactly. So 7 as a hexadecimal digit looks like this in binary, right? 1, 2 plus 4 is 7. So that's what a 7 looks like. And F, you know, is a 15 in decimal. That's 1 plus 2 plus 4 plus 8. That's an F. That's an F. That's an F. That's an F, and so on. So this number, 7 bunch of F's followed by E344, really looks like a whole bunch of ones. And then, you know, something more interesting for the last few bits. So E344, and it's not super significant. But that would be E344. But the notable thing is, you know, the beginning of this, 0 followed by a bunch of ones. What's significant about this binary number? 0 followed by a whole bunch of ones in every place out to the end of the number.
It's like the last integer.
Yeah,
the
it's like the biggest integer that you can have if you're doing 2's complement. Because when you go to this, that's the biggest negative number you can have if you're doing 2's complement. And if you're not doing 2's complements, let's just think about 4 bits, right? So just think about 4-bit numbers. Right, so there's the first 8. And there's the last 8. This number right here, this is sort of halfway through the range from all zeros to all ones. And this is significant. So if you're building a computer and you're going to have, say, 16 bytes of memory, you might decide, for example, that I'm going to put all my code in this upper half and I'm going to put all my data in this lower half. And if you're building a computer with 4 million bytes of memory, then this upper half, the first 2 billion bytes of memory, would go from location 0 up to this, 7 followed by a bunch of F's. And the second half of your memory would be 1 followed by a bunch of zeros up to all ones. And so, we have 64-bit machines, we have 64-bit addresses, and that's a lot of memory. That's 64 billion bytes of memory. Well, machines don't actually come with 64 billion bytes of main memory. But we kind of pretend they do. And what a lot of systems will do is they will say, okay, let's start at this address and work our way down and use this for temporary storage, local variables. And when I say something like integer I, that's a local variable. It's local to this function called main. And the address of that local variable is, 7 followed by a bunch of F's, E344. The local variable j is right next door to the local variable I. It's 7 a bunch of F's, E348. And the local variable k is right next to j. It's E34C. So what the compiler and linker have done is they've said, hey, let's store I, j, and k in memory near this magic address, 0 with a bunch of 1s. And anytime you see something with that address and the giveaway is the 7 followed by a bunch of F's, you're probably looking at a local variable. And you're actually looking at a variable in what's called the stack. If you've done Engineering 270 or you've played Magic the Gathering, you're familiar with the concept of a stack. But a stack is a type of data structure. We're going to talk about stacks in this course as a data structure. But it's an area of memory that usually starts around this location. Actually 7 F's with F's all the way through. All right, so we just printed out I, J, and P, and I and J were 10 and 20, and P was a weird number because it's this big long hex number. It's actually 48 bits, and as a decimal it prints out like that. All right, so what's going to happen if we say K equals star P? Remember, K is just some random value right now. But we're about to do K equals star P. And what's the value of K going to be after we do that? And why? So what is P equal to? I mean, not the number, but what's the significance of this number?
The address to I.
It's the address to I. So P is the location where I is stored.
So K is just going to be I.
So K is just going to be I. And you know, I can use the examine instruction and say examine this location in memory. And what's stored there is... Oh. Oh, that's weird. I glitched somewhere. Alright, I'm having a moment here. Well, let's just go ahead and do it. So we're going to do K equals star P. And if I print out K, K is equal to 10. And it's 10 because that was the value of I. So I is equal to, so there's K. I is equal to 10 right now. Now we're going to say star P equals 5, which says don't set P equal to 5. Go to the location that P is referring to and set that equal to 5. And P is referring to the same location where I is stored. So this is saying go to the location where I is stored and set that location's value equal to 5. So star P equals 5 is doing exactly the same thing as saying I equals 5. So if we set star P equal to 5 and then we print out I is now equal to 5. So we dereference this pointer and we use that as the destination to store this variable's value 5. And that changed the value of I. And P hasn't changed. P is still, 7FFF E344. But if we print what's stored at that location, we see the number 5. Right, just like if we examine that location, we see the number 5. Let's see, for note-taking purposes, a memory starting with address 7FFF can indicate it's a memory address of a local variable, correct? Yes, and this is not, a hard and fast rule, but just kind of for general working purposes, if you're in GDB and you look at a variable and you see an address that looks like this, it's probably a local variable, and it's probably stored on the stack. But that's just kind of a convention of what the compiler does, and it's something that you sort of discover by working with GDB with a particular compiler enough that you start to recognize that particular pattern. All right, so questions about this? So I can print the address of K, and it's E34C. If I print K, it's equal to 10. What if I were to print star K? What do you think that'll give us? Someone said error, so why would it give us an error? Yeah, so definitely either a segfault or some random number, and in fact it's going to give us an error. It's going to give us a segfault. Since K is equal to 10, star K is saying, no, don't print a 10. Go to memory location 10 and print what's there. And memory location 10 does not exist on my laptop. So when I print star K, it'll say cannot access memory address hex A, which is 10. If I try to examine that memory address using the X instruction, same error, can't access that memory address. Now if I say K equals ampersand P, so if I want to set variables in GDB, I can put them on the right side of a print command. So if I print out K, K is this weird number right now. But I can look at memory where K is stored. And it's you know, it's got something that looks like a memory address. So whether I have, you know, an integer or a pointer to an integer or a pointer to a character or something else, right? These are all just bits in memory. And looking in memory, you can't tell from what you're looking at whether what you're seeing is an integer or a character or a pointer to a double or a struct blah or something else. It's just bits, right? But when we're creating values for variables in a program, we know what those values represent. And it's up to us to keep track of that and make sure that what we're telling a computer to do goes along with what these variables actually mean. But the computer has no way of knowing, which is why, you know, if I have somebody's initial in a character and I try to treat that like a pointer, the compiler will generate code that will happily do that, and when it runs, it'll segfault. Because a character is not a memory address, it's a character, it's an ASCII code. But if I treat it like a memory address, for example, if I pass it as an argument to scanf, the code inside scan will say, oh, this must be a memory address, let me put something there, and it'll segfault. So on a good day, keeping track of, you know, variables and pointers to variables and arrays and things like that can be challenging. But it gets even hairier when we start dealing with dynamic memory. And the idea of dynamic memory is we're going to create variables as our program runs. We're going to create variables that don't exist before the program runs or in the beginning of the program. And so let's modify our main program. So I'm going to include another library called standardlib.h. So more test code here, right? IJK are integers. Yeah, it's a good thing we invented computers to manage this for us. So IJK are integers. P is a pointer to an integer. All right. And I'm going to print out the initial value of k, which should be some gibberish value. And I'm going to set the thing that p points to be 23. P is a pointer to an integer. I'm going to set the thing it points to be equal to 23. And I'm going to set k equal to the thing that p points to, and it should print out k equals 23 at the end. And when I run this, I'm going to get a seg fault. It printed out the initial value of k, but then it seg faulted. So this statement worked fine, but something between there and here went wonky. By the way, let me give you a freebie here. All right, when I ran my program before, it told me k equals this, and then it said seg fault. This time when I ran my program, it didn't print anything, it just said seg fault. And if I'm debugging this, especially at 3 in the morning, I'm going to think, hey, it's seg faulting before it even does this first print statement. And that's going to drive me nuts. So why did it seg fault before it printed that initial value of k? I mean, k is an integer. It's got some value. I haven't given it a value, but it's got some value. Why am I getting a seg fault before this print statement? We've touched on this in 224. Yeah, so it does not actually print what I ask it to until it sees a new line. So if I say print this out and I don't say put a \n, a new line at the end, it buffers this output. It executed this print statement just fine. And then it tried to execute this and it got a seg fault down here. But if I don't put a new line at the end of my print statement, when I look at my output, it looks like it died before it even got to that print statement. Right? That's a red herring. And it will cost you a lot of time trying to figure out, why is it crashing before my print statement? There's a bug in your debug statement, right? I put this print statement in to help debug my program. Well, there's a bug in there. The bug is I should have put a new line at the end of the print. So this is a little freebie advice, right? Always put new lines after your prints when you're debugging. And I've certainly lost many late night hours to forgetting to do that. All right, so if we've got our new lines after those, and then we run our main program, we can see, oh, it did do that first print statement, and then it got a seg fault. All right, so how do we find the seg fault? Go into GDB, start it off, do a next statement. There's our print. It printed that out. Do a next to execute line 9. That's where the seg fault occurs. All right, well, why are we getting a seg fault? We're trying to store a 23 at the location that P points to. What does P point to? Well, P is a 0. So there's a really good reason we're getting a seg fault. This statement is saying, hey, store a 23 at memory location 0. In other words, dereference a 0 and store a 23 there. Well, memory location 0 doesn't exist. So that's why we're getting a seg fault. All right, so we could set P equal to the address of I or J or K, like we did before. But suppose I don't have an I or a J or a K. Suppose I just want P to point somewhere valid where I can store a 23. And so this is where we're going to re-meet our best friend malloc. So malloc is a function we can call to request a chunk of memory. And the syntax is pretty straightforward. Just say p equals malloc. And we need to give it an argument which says how many bytes do we want to allocate. Well, I happen to know that an integer takes 4 bytes, and since I want p to point to an integer, and I'm going to store an integer value 23, and I'm going to copy that into k, which is an integer. I guess I do need an integer k. And then I'm going to print it as an integer, right? I know integers take 4 bytes, so I'm going to say, hey, allocate 4 bytes of memory for me. And let's set p equal to that. Okay, so we'll start off with k. K is a weird random value. Now we're going to set p equal to malloc 4. So let's look at the value of p before we do this. It's a 0. Once we execute the call to malloc, if I look at p, it's another big long memory address. But it's not an address that starts with a 7FFFF. It's an address that starts with a bunch of 5s. Well, on this system, in this operating system with this compiler, when I have an address with a bunch of 5s, that's not on the stack. That's not a local variable. That's in a different section of memory called a heap. We'll talk a little about heaps later. But it's a different section of memory, but it is a valid memory location. And I can examine what's at this location, for example. And I don't get a seg fault. There's a 0 stored there. In fact, there's a bunch of zeros stored around there. So when I said p equals malloc 4, p was set equal to this weird address. And now when I say store a 23 at the address stored in p, that should take a 23 and store it at this memory location. So let's go ahead and execute that. And now let's examine that memory location again. Guess what? It's got a 17 hex. That's decimal 23. So I've just created an integer variable on the fly. It's an integer stored at this location in memory. It's got a value of 17. And whereas k has some arbitrary value right now, once I say set k equal to the thing that p points to, k is equal to 23 now. So think about this. I've just created an integer while my program was running. When my program started, there was no predefined location to store this 23. But as my program executed, I called this function malloc. That gave me an address, right? This address right here. And that's where I stored my integer value 23. And if I call malloc again, it will give me a different address. And if I call it again, it will give me a still different address. And every time I call malloc, I get a different address. Well, these are locations in memory that I can do whatever I want with. So malloc is a system level call that basically says, hey, I'm looking for some memory. Can you spare 4 bytes in this case, because I'm saying malloc 4. And it gives me back a location and says, yeah, you can use 4 bytes starting at this location. Now if I say malloc 400, it gives me a very different address. And every time I call malloc, the system will find a chunk of memory, in this case 400 bytes of memory, contiguous bytes, and it'll tell me where in memory that block of storage starts. So we're going to use mallocs a lot because we're going to create things in memory that don't exist when our program starts running. We're going to create them as the program executes. And I put a 4 in here because I wanted enough space to store an integer. And I happen to know that integers take 4 bytes. But you know, if I run this on an Arduino processor, integers are only 2 bytes. And if I run this on a different type of machine, integers might default to 8 bytes. Well, they shouldn't under C, but you know, if I was doing something like a long, right, that could be 4 bytes, it could be 8 bytes, it could be 16 bytes. So I usually don't want to hardwire a number when I call malloc. What I want to do is use my sizeof and say I want the size of an int. And you've heard me say this in 224, I'll say it again here a lot. Don't ever use sizeof with a variable. Use it with a type, and only with a type. Don't say size of k, don't say size of star p, say size of int. I want to store an int. This is just telling me how many bytes an int takes. All right, so why do we want to do this? Why do we need to create variables while our program is running? Why can't we just declare all our variables in the beginning of our program like we've always done? And the answer is that sometimes you don't know how much data your program is going to encounter. If I know that my program is going to take a class of 30 students and calculate averages and things like that, I can make an array of 30 doubles, 30 strings, 30 ints, right? And I'm fine. But what if I'm writing a program that will let the user keep typing in information? They can just keep adding more and more information, and I don't know how much they're going to type. Right? If I don't know ahead of time how much data my program's going to deal with, there's no way I can declare enough variables or arrays that are large enough to store all the information that might need to be stored. So one reason we're going to want to use things like malloc is when we're writing a program and we don't know how much data is going to be processed up front. So let's talk about arrays again. And this is going to lead into your first programming assignment, which we'll talk about on Wednesday. But think about arrays. So, you know, if I say something like integer data bracket 10, I can store 10 integers in this one thing called data. Right? When I compile and link my program, the system sets aside enough space to store 10 integers. And I can get to all of those by using this variable named data. And I can say data bracket 0 or data bracket 1 or data bracket I. But this 10 is saying, hey, there's only enough space for 10 integers. And this is one problem with arrays. They're fixed in size. If I declare an array as an integer bracket 10, that array can only hold 10 integers. And if, you know, I've got overflow in my class and I've got 12 students instead of 10, I can't store the 11th and 12th students in this array. So that's one problem with arrays is they have a fixed size. And that's maybe the most direct motivation for why we're going to end up using things like malloc to find memory for storing things while our program's running. Because when the program's running, you know, maybe we see that there's, you know, an 11th and a 12th student that we need to store information on. And our code could say, okay, well, let's allocate some more memory so that we have spaces to store that additional information. But there's other reasons to want something more than an array. So let's talk about order of complexity. And so this is a topic we've touched on in other courses also. But the basic idea is, let's think about how complex certain operations are on a computer. And when we talk about complexity, we're not really interested in how many lines of code, because that depends on your programming language and your programming style and so on and so forth. If you write your program in assembly language, it's a lot more lines than if you write it in, Java. So we're not really thinking about, how long your program is. And we're not really thinking about how long it takes your program to run. Because if I run this program on a quad-core processor at 3 gigahertz, it's going to run a lot quicker than if I run it on my little PIC chip from Engineering 270 at 32K. So it's not the speed that's so important either. What we're mostly interested in when we think about the complexity of an algorithm, for example, is how the time changes based on changes in the problem size. In other words, if you double the amount of data, what happens to the time that it takes to execute? Whether it's taking a second on a very fast machine or 10 minutes on a very slow machine, we can ask the same question. If I were to run my algorithm on twice as much data, what happens to the time it takes? Does it double? Does it go up by 4x? Does it go up by 4,000x? Does it stay the same? This is the really interesting question. And this is the measure of complexity we're going to talk about in this course. So you have an algorithm, and you can run it on a certain set of data, and it takes a certain amount of time. And then you can ask, if I double the amount of data, what happens to the time it takes? If I quadruple the amount of data, what happens to the time it takes? And so we have this notation called big O notation. And we write big O parentheses and some sort of thing inside here that answers this question. How does the time required change as the amount of data changes? So if doubling the amount of data causes your algorithm to take twice as much time, that's linear, right? That's saying that, if you double the data, you double the time. If you triple the amount of data, you triple the amount of time. That's what we call order n. If doubling the amount of data quadruples the amount of time, that's quadratic. That's what we call order n squared. And so a bubble sort is an example of this. If a bubble sort of 100 pieces of data takes a second, a bubble sort of 1,000 pieces of data, right, 10 times as much, will take not 10 times as much time, but 100 times as much time. So order n squared looks like this. If you double the amount of data, it takes 4 times as long. If you get 3 times as much data, it takes 9 times as long. If you take 10 times as much data, it takes 100 times as long. Right, that's something that we call order n squared. And it's not a very happy place. Because if your data goes up by 1,000,000, the time required to run your algorithm goes up by 1 trillion. And your algorithm that worked great last week on a certain set of data and only took a second to run, well, next month you've got 1 million times more customers, you've got 1 million times the data to run your algorithm on. It's going to take you 1 trillion seconds while you're out of business. So order n squared is pretty horrible. Order n is nice. Order 1 is our dream. Order n, you can double the amount of data, it takes the same amount of time. You can triple the amount of data, it takes the same amount of time. You get 10 times as much data, it takes the same amount of time. You get 1 million times as much data, it takes the same amount of time. That's your dream algorithm. An algorithm that processes data, and no matter how much data you feed it, it always takes the same amount of time to finish. And this is always going to be a good thing. Maybe, you know, for a fixed amount of data it takes an hour, and maybe that's a really long time, but you know, if you've got 1 billion pieces of data and you can still crunch through it in an hour, or 1 trillion pieces of data and you can still crunch through it in an hour, eventually that's going to look really, really attractive. So order 1 is really nice. Order n we can live with. Order n squared we don't really like very much.
Is order 1 plausible?
Yeah, we'll look at some algorithms that are theoretically order 1, in particular hash tables. Will store and retrieve information in a fixed amount of time regardless of how much data you have. That's a theoretical performance.
Because this is kind of like a weird example, but like Google search takes seemingly the same amount of time no matter the results.
Isn't that awesome? That's part of why Google is Google. That's part of why, you know, they rule the planet right now. They came up with, they being 2 people, came up with, you know, a very efficient algorithm for doing search, you know, and adding heuristics to it and stuff like that. And yeah, I mean, if you were Google and you used a bubble sort to search for something, it might work great your first week in business. But, you know, eventually your customer base would grow and your performance would drop and drop and drop and people would stop using you. So the key, one of the keys to their success is, you know, they've achieved a really good order of complexity on their search. So yeah, we'll develop a hash algorithm that'll be theoretically order 1, but you know, it's pretty clearly not, you know, practically feasible in all cases that it would always take the same amount of time. But we can do a pretty good approximation. All right, n is pretty good. N squared we'd like to avoid because it's just a really kind of horrible growth rate. But there's worse. There's order n cubed algorithms. There's order n to the 4th algorithms. We get into matrix manipulations if you're doing 215, math 215. There's a lot of n cubed algorithms. There's algorithms that are order n to the n. There's algorithms that are order n factorial. These are horrifying, right? These severely limit how big your data is that you can run your algorithm on. And there's things that are better than this. There's log n algorithms. And this is a really nice performance factor, and we'll see a lot of algorithms this quarter that are log n performance. Meaning, for example, if you have 1 million times as much data, it only takes you 6 times as long. Log of 1 million is about 6. Usually when we do logs, they're log base 2. So 1 million would be 20. But still, you know, ballpark, really small compared to the growth of n. Alright, so the reason I'm introducing order of complexity now is because I want to use this to look at arrays. And I want to think about what we do with arrays. And 3 things we do is, you know, we add things to arrays, we remove things from arrays, and we search for things in arrays. So imagine, you're trying to save student scores. And let's suppose your students are numbered, 0, 1, 2, 3, 4, 5, up through n. And you get a score for student 7, you want to save that in your array, right? So we can add something to the array. Maybe a student, leaves the course, and so we want to remove their information from the array, or maybe we want to search for something in an array. And so I want to think about the complexity in time, the order of complexity of these different operations. And so let's just suppose I have a big integer array, right? Big enough to hold 1,000 things, and suppose that's more than I actually need. So remember in C, the funny thing about arrays is they don't have a fixed size. I can declare this to be an array of 1,000 things, but I have no way of knowing how many things I've stored in this array. So I always need to keep track of that separately. So let me call this length. So I could have a variable length that I initialize to 0, and when I store something in the array, I'll store it, in the next available spot in the array, and I'll increment length. All right. So what does my add routine look like? So add I. Well, if length tells me how many things are stored in my array, length also tells me where the next spot in my array is that I can store something. So if I want to add an integer I to my array, it takes a single statement. Data length plus plus equals I. So I'm using the current value of length. I'm storing my variable at that location in my array. And then I'm incrementing my length variable to record the fact that I've stored one more thing. So take a shot at telling me what's the order of complexity of this add function. In other words, if I rewrote my code and I said, okay, my array can now store 1,000,000 things instead of 1,000, so it's a 1,000 times larger data array, does this statement take any longer to execute?
No.
It doesn't. Right? This is an absolute order 1 algorithm. So adding something to an array really, really fast. All right, but let's look at search. Suppose I want to search for some value I, and I want to know, is this value I inside my array? Have I previously added that value to my array? Let me call this num so we don't get confused. So I want to know if num is stored in my array. Well, there's only really one way to do this, which is to make a loop. So I'll iterate from I equals 0 to the length, minus 1, and I'll say if data bracket I matches our number, let's return true. If I go all the way through my loop and I haven't found my number, I'll return false. So this is like pseudocode, right? But the algorithm to search for a number would basically be check everything in your array. Is the first thing equal to my number? Well, if it is, I'm done. Yeah, my number is in the array. If it's not, well, I got to check the second thing. Is the second thing equal to my number? If it is, I'm done. Yeah, it's in my array. If it's not, I got to check the third thing, and the fourth, and the fifth. If I've checked all the elements in my array and none of them were equal to my number, then and only then can I say, nope, that number is not in the array. So what's the complexity of this algorithm? If I change my array from 1,000 to 1,000,000, how does the time to execute this algorithm change? Does it change at all?
To the end.
Yeah. Worst case, this is order n. Worst case meaning I'm looking for something that's not in the array. Well, it's not going to know that until it's gone through all the elements in my array. And if my array is full and it's 1,000 elements, this is going to take, 1,000 iterations. If my array has 1,000,000 things in it, this is going to take 1,000,000 iterations. So this is linear. This is order n. Order n is not really great either. All right, how do we remove? So my length is equal to 8. Here's what's stored in my array so far. And let's say I want to remove 19. So how would I write my remove function?
Is there like a delete or something, or how do you even do?
Yeah, how do you even do? So before we could delete this number 19, we'd have to find it. So we're going to have to at least do what we did in the search. We're going to have to start at the beginning and say, is that a 19? Is that a 19? Is that a 19? Is that a 19? When we get here, we're going to say, okay, there's the number we want to delete. All right, so now we know we want to get rid of this. Well, what could we do to actually remove that from our array? And I'm just looking for kind of high-level algorithm ideas here. If you were doing this on paper and you had written down, a bunch of scores, and now you wanted to get rid of the 19 because it didn't count anymore, how could you do that on paper? I can think of at least 3 ways. All right, I'll tell you the first way. Yeah, go ahead.
How do we do what exactly? Sorry.
Get rid of that 19.
Oh, okay.
You got a list of numbers written down, and you want to just get rid of one of them.
Set it to empty and.
Yeah, I mean, the first thing we might do is just scratch it off. Just say ignore that number. Right? So we could do that. But then we're kind of wasting space. If this was written on a piece of paper, and we cross off each number we want to remove, well, we're running out of space, right? And the space corresponds to memory. So we could set it to some value, which means this number has been crossed off. But we'd like to be able to do this indefinitely. All right, so somebody suggested, I think, store all the values in a different array and then set each value from 3 to 7 according to the corresponding value in the second array. So effectively what that would do is basically move the 11 up here, move the 6 up here, move the 3 up here, move the 8 up here. And now we've sort of, squeezed out that empty space in the middle. And that's usually the way that we're going to end up doing this. There's a third option someone just suggested, which is, hey, since we're trying to get rid of this 19, let's just take this 8, copy that into here, and let's just reduce our length to say now there's only 7 things. Well, now, you know, there's our array of data. It's only got 7 elements in it, and it's got, you know, all the numbers we started with, except the 19 has been removed. So if we do that, that's an order 1 operation. If we do the previous suggestion, which is basically move everything down 1 spot, that's an order n. The order 1 is really, really super duper fast. Just take the last thing, put it in place of the thing you want to delete. But the order 1 changes the order of the things in the array. If the order is important, then we need to do this shift, and that's going to be an order n. So yeah, what somebody just said in chat. If the order is unimportant, we can do that order 1 deletion. If the order has to be preserved, then we're looking at an order n algorithm. All right, so we will go through these again. We'll rehash these tomorrow or Wednesday. These 3 array operations: add, search, and delete. And we'll make a table of their orders of complexity, and then we'll talk about how we can improve those. And that's going to lead us to our first data structure, which is something called a linked list. And a linked list is like an array, but it's an array that has better support for adding, searching, and deleting. All right, so we'll start from that on Wednesday. I will see you then, or if you're in CSE222A, I will see you at 1 o'clock. Otherwise, have a great afternoon.
See you in an hour.
All right.